In this video, we discuss how a thermal stress study can simulate the mechanical and thermal loads acting on a cast iron brake rotor and determine the resulting temperatures and stresses. This is an industrial brake rotor, much larger than the rotors on your car or truck. The simulation model is a 1/8 symmetry portion of the full rotor. Here we see the resultant stresses due to the applied mechanical and thermal loads. Let's take a step back and see what's required to set up and run this study. First, we need to create a new simulation study choosing the thermal stress analysis type. Let's go into the study settings and change the default stress-free temperature to 25 C. We'll also specify an absolute mesh size of 6 mm, which will give us two elements through the thinnest sections of the model. Of course, the production model includes the full rotor. We'll next go into the Simplify workspace to reduce the model to a 1/8 symmetry variant. Changes performed here have no effect on the production model. They are specific to the simulation process. Split the full model at each of the 3 global planes, which produces 8 separate bodies. Using symmetry gives us 2 advantages. First, the model size is reduced, which consumes less storage space and the solution time is decreased. And second, the application of constraints is very straightforward. We can fully constrain the model against motion in all 3 global directions without impeding the natural thermal expansion that we expect. Constraining thermal stress models can be tricky because over-constraint can result in severely exaggerated thermal stresses. Next, we determine which body is the one located at the nearest side in the first, or +x + y, quadrant. Then we keep this body and remove the other 7. We can now return to the simulation workspace. Notice that the model material has already been specified as gray cast iron, ASTM A48, grade 50. We'll keep this material for the thermal stress study. In simulation, when loads, constraints, and geometry are symmetrical, there is no motion in the direction normal to the plane of symmetry. So we constrain the following: the X translations on the faces lying along the YZ plane, the Y translations for faces along the XZ plane, and the Z translations for faces along the XY plane. Note that none of these constraints impede the radial or axial growth of the rotor as it heats up. Let's apply a pressure load of 13.8 megapascals at the hub bore to represent the load from the shrink fit between the shaft and rotor. This is the only mechanical load. The rotor is mounted to a water-cooled shaft, so we'll apply a fixed temperature of 38 C to this same face. We'll define a heat input of 36,500 watts per meter squared to the brake pad contact face. This value represents the average heat input to the rotor over time on a per unit area basis. The heat is generated as a result of friction between the pad and rotor when the braking force is applied. Lastly, we'll apply a convection load to all the exposed faces of the rotor, both interior and exterior, except for the brake pad contact face. This exclusion is conservative since we're ignoring the convective cooling along the portion of the face that's not covered by the brake pad. Do not apply thermal loads at the faces along the symmetry planes. Also, the program won't let you apply convection to the hub bore since we've already fixed the temperature of that face. The convection coefficient is 190 watts per meter Kelvin and the ambient air temperature is 25 C. This convection value is higher than you would specify for stagnant air with only buoyancy driving the convection. The value takes into account the spinning of the rotor and therefore the higher speed of the air flowing over and through it. The model is ready to solve. You can solve thermal stress simulations on the cloud or locally. When the solution finishes, the safety factor results are displayed. Notice the minimum safety factor is slightly more than 2.0 for the assumed conditions. Now we can toggle through the other available results, examining the von Mises stress, displacement, temperature, and heat flux. The area of greatest heat flux is where the slots are located. These openings allow cooling air into the rotor interior. Not surprisingly, this is also where the steepest temperature gradients and maximum stresses occur. Thank you for watching.